Yeah, so that was right. Current does. You're still looking at VGS, except current flows from source to drain. Okay. So that was the previous question. Determine the drain current of M1. So first off, what I'm going to do is I'm going to assume saturation. And my reasoning for doing that is because, oh, hey, we're given the current here. What? Oh, well, that's easy. Okay, so I hope you all can see what I'm talking about there. So we're given the value of this current source. No current's coming this way, so all the current has to go this way. So never mind. I1 is equal to 2 milliamperes. Done. B. Calculate the voltage VB across the DC current source. IB. Okay, now we're talking. So now we're actually going to need we're going to need the voltage here at any rate. And how can we get that? So, yeah, assume saturation and hope your hypothesis is correct. So, if there is 2 milliamperes coming through here, then what we would have is I is equal to 1/2 Kn V overdrive squared. 2 milliamperes is equal to 1/2, and then Kn is equal to 600 milliamperes per volt squared. And VOV is what we're looking for. So multiply by 2, divide by 600, we get that 4/600 volt squared is equal to VOV squared. And then 1/√6 times 2/10 V is equal to VOV. Interesting result. So that's 1/5√6 volts is equal to VOV. And VOV we can represent as V threshold minus VGS this time. Because what happens with the PMOS is you want your VGS. All right. I don't know. I don't think so. Is it possible? Is it possible that this is the drain and this is the source? Still? Then VGS. Okay, so then you can easily solve for VGS. I know VGS has to be negative. And so VGS is equal to negative 0.5 volts minus 1/5√6 volts. That's nice. And then, let's make sure that's true. Let's make sure that's true. Wait, no, that just makes VG and VGS the same node. So that's no good. I'm assuming it's the other way then. Fascinating. Oh, sure it does. Yeah, no problem. Right, because the current will lose voltage as it goes through here, as it goes through the transistor. So VG is going to be below VS, which is perfect, which is fine. I should not be hesitating so much. We can calculate that. So 1 divided by 5 root 6 gives you, nope, that's, okay. 1 divided by 5 root 6, this should be, that's more like it, 0.08. So you add the two negatives, you get negative 0.58 or so volts. And then that would mean that this is equal to 4.42 volts, right? Because this is the voltage of the gate, and we want this voltage difference to be 0.58. Okay. The 2 milliamps of current then proceed to pass through a 400 ohm resistor. So we can say that this voltage here, which we can call VB, is equal to, and I should move that down a little bit perhaps. VB is equal to 4.42 volts minus 2 milliamps times 0.4 kilo ohms, I'll say. VB is then equal to 4.42 volts minus 0.8 volts, and VB is equal to 3.62 volts. So we found the voltage here, and then we know the current passing through here, so we found the voltage here as well. Then what we can do, fascinating. The crazy part about all this is that this is what happened here is creating a current. So if there was no current here, your voltage would just be 0, right? Because no current passing through the resistor means that voltage is 0. Oh, never mind. Because then you would get a voltage SG, which means VD would go up. Oh, fascinating. Yeah, okay, never mind. This would be 5 volts then, if there was no current passing through here, because you would need VGS to be at least below 0.5 in order for there to be no current, and that would bring up this voltage. Okay, so sending a current does indeed lower the voltage here, which is good, which is what we expect. Calculate the maximum value of DC voltage Vx such that DC current I2 is equal to I1. So we know, I'm going to use the second paper here. We know I1 already. So we need I2 to be equal to 2 milliamperes. So 2 milliamperes is equal to 1/2 kNVOV squared, assuming that the other one's in saturation, which is a pretty fair assumption, especially since this one's in saturation. And so this would give you 600 microamperes per square volt. Right, so the equation is much the same. 4 over 600. Oh, I use milliamps instead of... Ooh. That's not good. Okay. This was microamperes, which means that that becomes 1 over 1,000. Then when you square root it, you get 100 root 10. So it becomes 50 square root 60. And hopefully that's not too bad. Actually, no, it's 1,000 on the top. 1,000 b squared. So the 10s cancel. You end up with root 10. And then root 10 over root 6 is the same as root 5 over root 3. So you get 2 root 3, nope, root 5. Root 5 over root 3. And then this becomes 2 root 5 over root 3. Sorry about that. 2 square root 5 divided by square root 3. And then you should, so this would be a negative value, you would subtract 0.5 volts from it, and you would end up with, funny how it was so close, 3.08 volts. And this becomes 3.08. Wait, becomes 5 minus 3.08. Very important. Which is 1.92, 1.92, and this becomes 1.12. There we go. All right, and that becomes 4 over 600 times 1,000 is equal to VOV squared. Square root that, you get same thing as before, which was 2 square root of 5 over 3 root 3 equal to VOV. How much time we got left? Not a lot. All right, let's go. And then you can solve for VOV. VOV is just, what are we looking for? What are we looking for? Oh, I see. Okay. Okay. So, when Vx becomes too high, then of course you're not going to get any current, right? Because that would mean, like, say it was VDD, right? Then you wouldn't get any current because there's no voltage drop. So, we know that this isn't true anymore. This is 1.92 volts. 1.92 volts. Right. So, right. Okay. This is S. This is G. You know that changing Vx doesn't change Vs nor Vg. Vg is set to be 1.92 volts and Vs is set to be VDD. So, so long you're in saturation, you're always going to get the same amount of current. However, the moment you leave saturation, then you will get less. Right? If you increase Vx enough, then you'll leave saturation. So this, you would get 2 milliamperes. And so your voltage drop across here would be 1.2 volts. Under typical circumstances, right. If this were in saturation, this voltage would be 1.92 volts as well. At maximum, right? You decrease it more. Hang on. If you decrease it, if this voltage goes below 1.92, if this was 1.5, then you would still get the same amount of current because this gate voltage is still 1.92. That's why you couldn't decrease this below 1.92, because if you put this at 1.5, then suddenly your VGS is higher and you get more current. But if you put this at 1.5, then you're still fine. So basically, your voltage difference across R2, assuming you are in saturation, is going to be 1.2 volts. 2 milliamperes times 600 ohms. Your maximum voltage that you could still be in saturation at is 1.92 volts here at the drain. So that means that the maximum value of Vx that you could possibly have, which stays in saturation, is this 1.92 volts minus 1.2 volts is equal to 0.72 volts. If you were to go any higher than that, then it would continue to send 2 milliamperes in until that 2 milliamperes would be blocked by the resistor, because this voltage was 1.92 and this voltage was 1.2. Yes. Okay, that was me. I'll try to clear up that explanation. So, what do we know? What do we know? We know that VD minus in saturation. No, that's always true. VD minus Vx is equal to I through the transistor, for some reason they call it ID, times 600 ohms. In saturation, ID is 2 milliamperes, which means that VD minus 2 milliamperes times 600 ohms is equal to Vx. And the maximum value of VD that we can have, and stay in saturation is 1.92 volts. So let's assume we're at the cutoff and see what value of Vx is. So we'll say 1.92 volts minus 1.2 volts is equal to Vx, which means that 0.72 volts equals Vx at the cutoff. All right, now let me do one more. That's a monstrosity, and there's no way we get something that tough.